Hello everyone, I hope I'm audible to you. So I'm one of your, thanks. I'm one of your course instructor. I'm Basamati. So today we will be seeing some overview of the week 2 content. If you would have looked upon, it would be easy for you. Otherwise, we can discuss it here. No problem. Let me share this screen. My screen is visible. Today, last week, I hope you would have learned some content on the basic things of the control systems, how the signals would be, what are the properties, what are the time domain specifications and all that. So this week we are going to see some basics on signals that has been useful for that has been a good tool for control systems. So how we are going to use these signals and how we are going to any control system engineers, that overview we are going to see in this lectures. So for an introduction, I am going to start with the last week content, where you are familiar with this control loop setup, right? So where there will be a reference signal. Always this control systems can be classified as an open loop, where there is no feedback loop. You will give only one input and you would expect one output to come out of the system. And the next thing is this closed loop system, where you will give input and there will be an output that will be feedback to this system, where the corrective measures will be taken here and the system make the corrections and give the necessary output as you expected. These are all the two different basic systems, control systems that has been in practice. Okay, so if you see this plant, this is an example of a closed loop control system, where it involves different parameters like reference signals and the control signal, disturbances, and this reference signal is the input side, and we are expecting some signal as in the output side, where when we give the feedback, it also have a sensor, and the sensor has some inherent noises. So these are all some additional parameters with respect to this closed loop control system. Here we are going to learn different types of signals other than the system, and how we are going to combine the signals with the systems. Okay. First thing is reference signal. Whatever signal you are giving as input are termed as reference signals or desired signal. How you want the system to behave or what you want the system to track, that is called the reference signals. Control signal in the sense, based on this reference signal, how well you are going to control your system, that is a control signal. For example, I am giving a 230 volt for my fan and I expect it to run at 200 rpm. So this is a open loop system. Let's take this is a open loop system. I am giving 230 volt as an input and I am expecting my system to run at 200 rpm ideally, but in ideal scenario this won't happen. This might run at 180 rpm or 250 rpm, but it never runs at 200 rpm, as this is a physical system, physical properties of the system. There will always be a decay, there will be a loss. It's a mechanical system, so we cannot expect it to work very ideally based on our mathematical equations, right? So in order to look for this deviations from our desired output to the actual output, we are going to take this as a feedback and give back to the control system, where this control system will see how much we are going to change the input so that I will get this desired response. So you cannot expect that I will always give 230 volt and I should get 200 rpm. It's not like that. If I want to get 200 rpm, how much input I should deviate, how much input I should change. That's how this control system works. So that signal, the deviation from your desired to control signal, the actual signal you want to give to make the system work in your preferred way is this control system signal. There will be some problem in the system itself. There will be some physical damages or some external disturbances, that we call it as disturbances signal. In the case of example of a fan, the fan's blade might be not in a good condition, it may be deformed, so this is a one type of disturbances. Or the wind outside the window would be very heavy or too fast than the actual temperature or the wind inside this room, so that may be another disturbance. So whatever force you are giving to the fan, that might be opposed by the wind from outside during hurricane or something. So this is the disturbances signal. Disturbances can be inside from the plant or outside, that is external or internal disturbances. The next one is this noise, how we are going to see this noise. Noise in the sense, I have a sensor that I have very cheap sensor. I didn't give much price to buy this sensor. So when I'm inserting the sensor into the fan, like a kind of tachometer you can imagine. So when I insert, actually it is running at 280 rpm, let's say, but the sensor is showing 250 rpm. But if I replace this sensor with a good one, like high quality sensor, then it will show 280 rpm. Then in this concept or in this scenario, the sensor is noisy. This cannot be termed as disturbance in the plant. So even if you change the sensor, if all the sensors give the same reading, but it is not at the actual reading, then it is termed as disturbance. This is the very intuitive difference between the disturbances and the noise. Everybody will get confused in this aspect, right? What is disturbances, what is noise? Both will be seem to be same, but these are all the basic differences between the disturbances and noise in terms of control system. Clear? Any doubt in this? If you are okay with this definition, you can give a thumbs up so that I will know whether you understand or not. No. No. Thank you. What about Jamilat and Dhruv? Are you listening? So this should be an interactive session. The objective of this session is to make you speak aloud, because we don't know where you stuck or what problems or what are the doubts you have in the session. This is going to be very interactive, so please feel free to speak whatever you think. Okay? So these are some definitions of the signals we are going to use so far, so you should be clear in this so that this won't affect the further learning. Okay. So yeah, it's very similar. Yes. If you learn signals and system, this the content would be very easy for you. Okay, this is another form why we are learning the signals, why we are very interested about the signals domain, because if I take a plant like this, so if I want to, as I said, there will be a fan, and if I want to, if I am giving an input and I want the output to be similar to that. For example, if I give 120 volt, I would expect my output to be 100 rpm. So that this 100 rpm is this imitation of this 120 volt, right? So whenever I am giving 120 volt, I am expected to get 100 rpm. So if I change this to 220 volt, I will expect some other some 240 rpm. I would expect some really relationship you can assume. So I want the system to track the input. So if I give, for example, if I am giving my RFT reference signal as 1, my output should follow this. This is my objective here. So why this is very important in a control system is that for some systems, for example, some process control system, sometimes it is very difficult to identify what the system is expected to give as a result. So in that case, we will try to make the system to track the input, whatever we are giving. So whenever we are expecting tracking means the system output should track the input. That's what the objective is. For example, if I give an input like this, so if I say I want to track the system output, I would expect my output like this, right? It should exactly track the output, then only I can say my system is very good and it is tracking it very properly. But ideally it won't be in the case in the ideal system because of the physical properties of the system. So it may experience some delays, it may experience some overshoot, but ultimately if we can track this output properly, that is okay. But we have to design control systems such that this overshoot and this delay won't affect us too much. Okay, within a 2 seconds or within a second based on my requirement, if the system can track the input properly, that is enough for me. But if this becomes like this, or if the delay becomes like this, then this would be a problem for me. So how much we can reduce this overshoot or how much we can reduce the delay, that matters. That's how good we are going to design our control systems. Okay? So this is one practical example we want to say. If I give a position, if I pedal, if I press the gas or if I press the accelerometer in my vehicle, I expect the vehicle to go at a particular speed. So for example, if I am giving this much engine force, 1000 engine force, I expect the vehicle to track 20. I expect the vehicle to go at a 20 meter per second or kilometer per hour. Okay? But here comes the problem is, ideally the system is good if the plant is good, it is not, it is free of any disturbances, the system will behave like that. The system will give 200 kilometer per hour. We will keep the unit in 2 kilometer per hour, 200 kilometer per hour. But when disturbances or any external things, for example any bump in the road or any drag or any deformity in the car is there, in that cases this will affect the system output. Although you give 1000 engine force to the vehicle, the system won't behave as you expect. There will be some deviations in the system. This is in case of open. There is no other way to correct these things. There is no other help you can do to correct the system. It will be there like that forever until the disturbance is present in the system. But why do we need a closed loop architecture? To control this, to make the system output in our desired way, we are analyzing what the output is and taking care of this output and bringing it back to the system. The system should be aware of what output it is giving. The controller or the control architecture we are building should be aware of the output it is giving. So based on that awareness, we are going to build upon this system characteristics. So for that, so for example, this is my plant. Here this is the car, the plant is the car, right? So this is a controller I design, whatever controller. If you are familiar with the controller, it can be PID controller, bank controller, or any other X controller we can think of it. So this is a feedback. For example, I am giving 1000 engine force and I am expecting 20 kilometer per hour for the vehicle to achieve. But it is not, because of the disturbances. If you see here, it is going down to around 5. Okay, so I am considering there is a disturbances in the system. So here instead of 10, this is 5. Now it is 5 kilometer per hour. So I am giving this 5 kilometer per hour back to the input. So my reference is 1000 and my reference is 1000 and I am getting the output as 5 kilometer per hour instead of sorry 20 km per hour for giving 1000 inputs. So what this controller will do is it will try to find the relation between this input and the output, so that what input I should change so that I will get this, I will make this 5 to 20. That deviations, that control actions, this controller will give back to the plant, so that the input will change to some 1000-2500 let's say. So here you can see this is the input I am giving, ideal input, but this is the control input, we will come to this here. So this is the measured output I am getting some deviation, some overshoots, and this is the error. So at first when I am giving 1000 input, I am getting 5 km per hour. So the error would be so much, so high at this point. So the control action should be 0 at this point. There is no control action. So once I started giving the control action, and I can see the reduction in the error, right? So that I can see the deviation getting reduced in the measurement. So that's how it will, after giving another feedback, it will try to make 5 to 10, it will try to make 10 to 12, then 12 to 15, kind of. Based on your control input action, it will at last try to make 15 to 20. So once it reaches 20, whatever desired we have, and then the control action becomes stable. It won't change at all. So if there is any further disturbances, then the control action will again change. So this is how this will happen. So here you can see, so this is the time taken for the control action to apply. So there is we gave an input 1000 engine RPM, engine force. So we got some good output around 20. Some disturbances happen at this place, so there will be a deviation. The value went down, and this time the control action was taken. So it is brought back to 20 km per hour, where this is not in the case of open loop. Where in the open loop, once it went down, it went down forever. It cannot be taken back to the desired response. So this is the one good thing about the closed loop control. In terms of disturbances, how well we will be able to regulate the system. Okay, but sometimes there will be this is one of the disadvantages of the system. Sometimes we cannot make this error goes down, or we cannot bring back the system to the desired response. The error will be always constant, and for example, if this is the desired response and there some disturbances happen, but the control action is trying to take it back to the original system, but at some point, because of the nature of the controller you designed or some mistakes in the controller, this won't be able to bring it back to the 20. This might be around 10 km, 18 km per hour forever. You cannot. So then you should redefine your controller. You should try to remodel your controller. There might be some mistakes in the controller. So this kind of problem is called as tracking error in the system. The error will be constant and you cannot do anything on this point. Then stabilization effect. So sometimes when you design a controller, there will be some if the input is not set, you heard of DO stable, right? Bounded input, bounded output. If the system is stable, whenever you give bounded input, for example, finite input, you would always get a finite output. That is meaning of finite bounded input output. So sometimes when a system or when the controller is not designed properly, or there will be a problem in the designing, there might be a overshoot, or there might be some unstable behavior of the system. The proper controller should make the system go to a stable region. It should not oscillate, or it should not grow exponentially forever. So that is a good way to design a controller. So a signal, how we can generalize using the signal. Signal can be interpreted as a function that conveys information about the behavior or characteristics of any systems. So noise can also be a signal, but the noise is unwanted behavior. So we don't bother about the noise. We just want to eradicate the noise. That's how we work on this. So there are different kinds of signals, analog, digital signals. So I think you will be very familiar with this. Whenever it is analog signal, it will change from point to point. If it is a digital signal, it will be like 0 or 1, either 0 or it is 1. 0 means off, 1 means on. and it could be continuous, discrete. Continuous in the sense at each point of time, whatever minute deviations you take, you will always get a value in that point. That is called as a continuous function. But discrete in the sense it will be available, the signal will be available at some particular points or at some particular chunks of time. You would not expect it to, if I want to find whether there is any signal in 14.5, I will not be able to see that. So there are different applications for both continuous and discrete types of signals. Deterministic in the sense the signals are unambiguous. There will not be any uncertainties in the systems. Stochastic or non-deterministic signals are not a straight away signals, can be corrupted with noise. We have to give some, we have to do some tools or some algorithms to extract the original signal value. So this cannot be predicted precisely from the past behavior. That's how we define a non-deterministic signal. And the even signal or odd signal in this sense, even signals will be symmetric. So if we say at time t equal to 5, let's say I have my signal's value is 10, my signal amplitude is 10. So when we say when time t equal to -5, then also it will be, the amplitude will be 0. So this x of minus t will be equal to x of t. Where in odd signals, x of minus t will be equal to minus of x of t. It's kind of a mirror. That is called as a odd signals. This will be useful while you apply some properties on those signals. These are these terms. So periodic signal would be, it repeats after some particular time interval. The pattern of the signals will be repeating after particular time interval. Where the aperiodic signal, you would not expect that behavior. It is random. Okay, so this is the gist of the lecture 1 and the V2. So far, do you have any doubts? If you have any doubt, please raise your hand. We can discuss. Otherwise, give us a thumbs up. Okay. Rest of the people? Do you have any doubt? Or it was not audible when you turn on the mic? Oh, thank you. We'll go to lecture 3. So at the end of this session, you will have some quiz games. So be alert or ask some questions that will be helpful for the quiz. Okay, then comes the recall of convolution integral. Is anybody is not aware of what is convolution here? Feel free to raise it. Or you want me to touch upon that? Yes, yes. First, I will start off with what we are going to see using this time and frequency domain characteristics. Okay? So there are different types of domains where we utilize these signals, where we use these signals based on our convenience. Some people use all the tools in time domains, some people use in frequency domains. Each domain has its own advantages and disadvantages. For example, time domain in the sense you would know at this particular time how the signal is. Frequency domain will give how much of the signal is there in this particular frequency. So for example, at a frequency of 100 there are 5 signals, but in time domain at time 5 what is the amplitude or what is the nature of the signal, whether it is too high or whether it is too low, that kind of interpretations. These are like not same but different. These are completely different with respect to the application. Whatever application you need, you can choose it. Nothing is good, nothing is bad here. Okay, And in time domain, you would, as I said, you would represent the time in terms of signal in terms of time, but in frequency domain, you would represent the signal in terms of magnitude and phase. How efficient or how magnificent is it, and how much it is with respect to the phase. For example, is it whether it is positive or whether it is clockwise or anti-clockwise, all those interpretation you can get from this frequency domain signals. So this is one example where you see these are all two signals, sine of t plus pi by 3 to sine of 2t. So this is the visual representation of this signal. If you see this Desmos, if you are interested in this, you can go to this website and you can give whatever signals you want to visualize. Sometimes we know how it is. For example, we know how sine t looks like, right? It will be like this. Based on the t, we know how the cos look like. We know how the tan looks. But if I say sine of 2t plus cos of 2, 3t plus tan of 4t, how will you say how well this would be looking? All of a sudden we don't get this visualization, right? So to visualize that, you can use this website where it will be very interesting to see how the signals look like. So this is the visual representation of the signal x of t mentioned here. So it is represented in time domain, so it is in t, right? So at t equal to 0, you can say my magnitude is 0.86. At t equal to pi by 6, my magnitude is 2.7. This kind of interpretation you can get from the time domain. But if I want to represent this in a frequency domain, how will I represent? The time domain signals can be represented in frequency domain with this representation: a sin omega t plus pi, where a is the magnitude of the signal and omega t is the frequency of the signal, and omega is the frequency of the signal and pi is the phase of the signal. Okay. So for example, I have separated this signal into sin t plus pi by 3 into and 2 sin 2t. This signal separately one and this signal is another one. So how we are going to represent this? Since the magnitude, this is the magnitude. So the first signal magnitude is 1. So this is the first signal's magnitude, sin of t plus pi by 3. And the magnitude of second signal is 2. So we have represented this as 2. Okay, sine of 2 sine of 2, where the frequency is this t is equal to 2 pi. So when you represent t is equal to 1 by f, right? So if you want to represent, this will be 1 by 2 pi. So when I say omega equal to, here omega equal to 1, here omega equal to 1, here omega equal to 2. So if I want to represent this, this will be 1 by 2 pi, this will be 1 by pi. So the first signal will be 1 by pi, first signal will be 1 by 2 pi and the second signal will be 1 by pi. How we are going to, so we represented a, we represent the omega in the graph. How we are going to represent this pi? So if there are any additional terms, you should look for it. So the first signal, there are some additional term, that is pi by 3. So the first signal, that is at 1 by 2 pi, this one, what is 1 by 2 pi is at pi by 3 magnitude of phase magnitude, okay? But in the second signal, there is no additional term, that is 0. So the second signal, that is clear. So this is how we represent the time domain signal into the frequency domain. So here you can see at this frequency how much how efficient the signal is, what is the magnitude of the signal. But whereas in the time domain, at this time, what is the magnitude of this signal? That's how we see. So if there is some other signal that is in the same frequency, you would expect here. That will be mentioned here. Okay. So these are some example where these are sine magnitude 0.5, you can see here. Here, of 120, this comes under 120. So this is how you represent a signal. That is, added signal is basically you are just adding all the magnitudes and time frequency to it. We will come to the convolution part. I understood that I need to give some basics on that. Before that, if I want to represent what is convolution, we need to know what are all the basic signals that involves in signals and system and for control systems. First important thing is unit impulse. Whenever there is a term called unit, you would assume that the magnitude will be always 1. Impulse signal. Impulse signal, can you give an example for an impulse signal? If you already know. Real life example. It need not to be unit, but any impulse signal. What? Push button, yeah, that could be a good answer. Impulse signal is in the sense at that time instance, whatever time instant you are making that action, at that time instant there will be some signal. Other than that, there won't be. The good real life example is lightning or thunder. So at that moment, the magnitude will be too large, and after that it won't be visible. It won't be there in the system. That is an example of the impulse signal. At that point, push button is another example. When you push the button, the energy will be released. After that, it won't be there. And the unit step means on-off switch. When you turn it on, it will be on forever. When you turn it off, it will go off. So until the point I turn it on, it will be 0. When I turn it on, it will become 1. That is the step function. When the magnitude is 1, we will call it as unit step function. We can represent this as like this. When t less than 0, when we are speaking about the unit step function, always it starts at 0th time. So when t less than 0, it will be off. T greater than 1, it will be on. So 1. Okay. The next signal is this ramp signal. I'll come to this. And the next function is the ramp function, where you find some linear increment in the function forever. It will keep increasing. It's an exponential but linearly increasing function with respect to the time. When time increases, the magnitude also increases in a linear relationship. That is a unit ramp function. So it will be represented as when t equal to 0, it will be 0. For t greater than 0, whatever t varies, that's how the signal also varies. Okay. Some basic relationship between these text signals are given here. One is how impulse is varied from step. So as I said, at that particular time, impulse will be high, but for a step, the impulse will be there forever, right? The signal will be there forever. Right? This is a mathematical representation that you can learn from the video, but I want you to think intuitively how we can connect these two things. So at 0 point, I have an impulse signal. At 1 point, I have an impulse signal. At 2, I have an impulse signal. So if I discretely keep on adding something to infinite time, can I say this is a step signal? Yeah. So that's what mathematical representation also tells us. So if you integrate the impulse signal, you would get a step signal. If you integrate the step signal, you will get ramp. If you integrate ramp, you will get parabol. On the other hand, if you differentiate step, you will get impulse. Here's what it is. So since impulse signal is a single magnitude signal, right? It's not a function. When you differentiate this, you would end up having 0. There is no change in that signal for an impulse signal. But if you differentiate this unit step signal at every point of time, you would end up having each impulse signal at that particular time, right? So that's how. So if you differentiate a unit step signal, you will integrate. I will write it properly. Here, impulse, step, ramp, parabol. These are some famous signals we used to use. I explained until ramp. Parabolic is like this. You would have noticed this in the mathematical courses. So this is integration, integration, integration. So let's see this differentiation, differentiation and differentiation. Right? So when you integrate an impulse, you will get step, ramp, parabola. When you go for differentiation, you would get the upside signals. So this is the basic relationship between your test signals. So you can get one signal from other signal, right? You can just use this mathematical tool if you have only one signal, one application. Signals will be available always, but when it goes to an application, you have some hardware setup that can generate only the impulse signals. So in that time, you can accumulate all those things and generate a unit step signal. That's how I want to interpret this. Okay, you should know all those things. And then, what is an impulse response? So this is where the convolution comes into action. So convolution basically represents how an input signal is modified by any system. If I give a system, if I have a system, I am giving one input and I am getting an output. So this convolution represents how the system is modifying this input signal to get the particular output. That's what the convolution represents. It is a weighted overlap of an input with flipped and shifted version. But this works only for the LTI system. Please do keep this in mind. So when I give an input, I would expect my output. This can be a flipped. For example, this could be x of minus t, or this could be shifted version of x of t plus tau, or x of t minus tau. So based on the system property, the system can do shifting or multiplication, or shifting and multiplication. So if you get an output, if you have some output and if you give some input, if you have the knowledge of these two, if it is a LTI system, you would be able to find what the system looks like. So this how effective it is, the convolution. Based on this convolution property, you would say how the system looks like. Okay. The mathematical representation of the convolution looks like this. Okay. You will have a input, and you will get an output. Some impulse actions you will take, that is a multiplication and shifting of the original system. See, convolution is a mathematical way of combining two signals to get a third signal. This can also be applied like this. The convolution integral measures the area overlap of one signal as it is time shifted over the other in the x of t. For example, if this is mere representation of this equation, that is nothing sounds good than that, but the idea behind it is like that, how the system is modifying the input. That's what you have to keep in mind. This is used to express the relationship between the input and output of the LTI system. This works only for the LTI, not for linear time variant system. Okay. So these are all some properties of why we are learning this property, in the sense based on this properties. This is a kind of shortcut to your system. If you know this property, you can just straight away use some standard signals to find the system responses easily. That's why this makes our job easy. That's why we are learning this. Convolution is inherently commutative. Commutative in the sense, what if you multiply signal 1 with 2, that will give the same answer with if you multiply this signal 2 with 1. For example, sine into cos and cos into sine will give the same. And the distributive property tells, if you add two signals and multiply with it, and if you multiply two signals and finally add with it, this both will give the same results. Associative in the sense, instead of this multiplication, even if you, what is the order of your multiplication? Mix and match of the signals. Shifting property tells us, whenever one signal is time shifted, your output will also be time shifted. Right, whatever it is. Whatever signal, whatever out of it, it will be time shifted. If both input signals are time shifted, the time shifting will be enabled in both, the time shifting will be seen in the output, right? If one is time shifted, only that time shift will be visible in the output. If both are time shifted, both time delays will be visible in the output. That is shifting property. Scaling property is kind of scalar multiplication. Whenever you are multiplying the time at which the signal is there, it's not a into x, it's x into a. Okay, if you are multiplying the time at which the signal is being applied, then this is the relation between these two. The output into the signal will be divided by the 1 upon the magnitude, modulus of the magnitude. Okay, so there is a if I say this is one signal I have, okay, until -2 to 2 I have turned on the signal, kind of step you can see, but for some interval step signal for some interval I have turned on, and I have another impulse signals. If I want to convolute these two, if I want to see how this system output will be, so this impulse response is based on my system, and this is the input signal I am giving. So how this convolution looks like is that it is not bothered by it at all, because this is a single system, and at this point this is also active, so it won't bother my system's output at all. It will be as it is. My system input will be same as my system output. But when this impulse response is time shifted, instead of giving this impulse at 1, I am giving it with a delay of -1. What if it? So when we saw this, right, shifting property, when there is some time delay in the input signal, there will be the same time delay in the output signal also. So there will be some same time delay in the output signal also. If this is time shifted by -1, if this is time shifted by -1, this will also be time shifted by -1, -2 to -1. If this is time shifted by +1, this will also be time shifted by +1. So, clear? This is just application of the convolution properties we have learned so far to make you understand, visualize. And what is convolution of two signals would look like? Convolution of two step signal will give a ramp signal. Before that we have studied similar thing. Can you recall it? To derive one signal from other signals, how did we do that? Using one signal, how did we derive other signals before? We have seen that. Yes, using integration we have derived, I'm taking integration. So how did we get the ramp signal from integration? Integrating the step signal. Here only one signal involves, right? There is no two signals. Here there are two signals we are involved in. How can you relate? Is it confusing you? Both of these things, how we can interpret this? Anybody is getting confused here? It is very, very similar or same. Convolution is also like kind of integration. Both are closely related. In fact, convolution with unit step is equivalent to the integration here. So this involves like integrating multiple step signal. That's what we are also doing. Instead of doing multiple, I'm just visualizing by two signal. That's it. Okay. I'm not saying both are same. Both are closely related. Okay. So from this, can you say convolution of two ramp signal, what it would be? You can type it in the chat box. Convolution of two ramp signals, what that will give? Parabolic signal, yeah. If anyone have any doubt in this? So this is how we are using convolution as a tool to represent two different signal, to use two different signal to get a third signal, or to identify what the system behavior is when I am giving some random input, I am getting some random output, how we are going to connect this input and the output, and to know what the system is actually doing itself. So these are all the things can be connected by a single point called convolution. This is a tool. Convolution is a tool. It's not a system, or it is not a object. It's a property or a tool to identify these things. So if I ask you some questions on this, how convolution is useful, or where you are going to use, can you clearly state the statements? This is used to generate third signal from two different signals, or it is used to relate the input to the output, right? These 2 points are clear. Okay. If it is clear, please everyone please give a thumbs up. We will move forward to the next. Right, rest of the people. Vinay, Arun. You are with me, right? Vinay? Yeah. Have you been running around? Okay. So you are clear with convolution. Everybody is clear with convolution, right? Okay. I'm going to read lecture 3. Where it involves Laplace transform. This is another important tool apart from the Fourier transform. This will give us another dimension. This is the example we saw so far, how it is being represented in the frequency domain. Okay. In order to go to Laplace transform, we will first touch upon what is Fourier transform. So Fourier have stated that in any signal in time domain can be represented as a summation of sinusoids of different frequencies. So if you want to represent this signal, you can represent the summation of sinusoids of different frequencies, for example this. So when we subtract these two, you will get some signal basis. So in any form of signals in time domain can be represented by the summation of sinusoids of different frequencies. Okay, that's what the Fourier transform is used for. So sinusoid, why do we particularly preferring to sinusoid is that they do not change shape when you pass this to the LTE system. This is one of the good properties of the LTE system. LTE system don't alter the signal shape, particularly when you give sinusoid signal. Okay, the LTE system may alter it, but LTE system will not alter it when you give a sinusoidal system, whatever the system behavior is. And each domain of a signal representation provided with different kinds of information. So based on our application, we will try to change this. Okay. So this is one example where we start up with a RL circuit where it involves one resistor and one inductor. So if we want to write the equation of the circuit using KVL or KCL, so I will start up with this point, or this point I will start up. So I will get this IR. If I want to represent the voltage around this region, I will do V equal to I into R, that is I into resistance or whatever resistance across this. Here it is I, since the resistance is 1. And the next thing is how we are representing the voltage across the inductor would be L into dI by dt. if I want to close this circuits, V across R plus V across L should be equal to 0, right? In a closed loop circuit, the summation of all the voltage should be equal to 0. So this V across L di by dt, the representation for the voltage across inductor would be L into di by dt, because the inductance at a particular time instance how the current should be. That is a multiplication of these two. So this should be 0. This is the inherent equation of this. So if I rearrange this equation, if I take the L here, and it would look like this. So if I differentiate it and find the solution for this equation, I would get some solution like this, which end up having, if I want to plot this current, it would look like this. Why? Because there is a minus term here. It's a decaying exponential signal. Okay, it's a decaying exponential signal. So similarly, if you want to see how to, the question here is how to verify whether the above expression is a solution to the differential equation. This, how to express or how to say this is the proper solution, or this is the proper solution for this differential equations. For this, this Laplace transform would be one possible solution. So this is another example. If wanted, we will come back here. This is the same like circuit. Okay. For this kind of problem, Laplace transform would be one viable solution. So some real-time example if you want to see, that is, these are all the responses of a simple pendulum at different phases. Everybody know about what is under-damped, undamped, over-damped systems. If you don't know, give an inverted thumbs up. If you know, gives a thumbs up. Okay. Everybody else? Okay. Okay. As most of you gives inverted thumbs up, we will see what is under-damped systems. Generally, we will say there are different orders of the system. If you see orders of the system, orders will be equal to how many energy elements present in that system. Energy storing element, okay? Not energy elements, it's the energy storing element. For example, if there is an inductor, there will be one energy storing element. If there is a capacitor, there will be one. So likewise, based on the number of energy storing element, if there are two inductors, that will be counted as two energy storing elements. Based on the number of energy storing elements, the order of the system will be. So order will be equal to energy storing element, right? Likewise, if it has one energy storing element, it's first order system. If it is 2, then this is second order system. So if it is 3, third order, and after this we will call it as higher order system. We won't particularly see how the system behaves. We will be interested in all these three systems only. First, second and third order system. And the second order system particularly exhibits very interesting behavior. For example, if there are two energy storing elements in that system, it behaves very interestingly from the rest of the other system. So we can represent this into a mathematical equation like this. For example, dx t square x by dt square plus 2 zeta omega n dx by dt plus omega n square x is equal to 0. So in this representation, this tau belongs to the damping ratio. We call this tau as damping ratio, and this omega is as a natural frequency. Why these two are important in the sense, the system that stores energy should need all these things. How the energy storing element behaves, that is the main idea of this of studying how the system, second order system behaves. So if the damping, for example, you have a door, at your house where the room is a AC room. So the doors are automatic doors with spring. Okay, if you open it, it will automatically close by itself. It's not sensor based. I'm speaking about mechanical closing of doors. There will be some spring attached to the door at the top, right? So if you leave the door, it will automatically close. So based on how well it is closing, how well the doors are closing and not letting the AC out of the room, this damping will be, we can say the damping is good or bad. For example, if I open the door, come into the room and leave the door as it is, I'm not pushing, I'm not leaving anything, I'm not giving any force. So how quick the door can come into the frame and lock as much as possible. If there is some, if the door is coming at very low pace, or example very slow, we call it as over damped response. Or if the door comes very quickly and slam, but it is not letting any AC out of the system, then it is critically damped. If the door comes very quick and goes out with the force it comes and slammed, then we call it as under damped system. So based on this behavior of the damping, or based on the behavior of the spring, how well it is being able to come to the point where it closes and not letting the AC out, we call this as different names. First name is undamped. Undamped in the sense there is no spring at all. We don't have any spring, we have to push it back. Another one is underdamped. Undamped is different from underdamped, there is difference. Then critically damped, then overdamped. So based on this I told the story based on some real-time scenario, but mathematically how we will represent this is undamped in the sense this tau is zeta, this is zeta, okay, not tau. This zeta I represented here should be 0. Ideally there is no damping at all. Then that is undamped. There will not be any energy loss, or there will not be anything that keeps the thing out of the way. Underdamped in the sense, in this case, the zeta value will be lesser than 0, greater than 0 but lesser than 1. In terms, when it is critically damped, the zeta value will be exactly equal to 1. It is ideal case. When it is overdamped, the zeta will be greater than 1. It is unwanted. Okay. Now I will say how the scenario looks like. If the system is undamped, then the system will keep on vibrating. It will never settle forever. It will keep vibrating forever. Underdamped in the sense, it behaves on oscillatory response. It might be oscillating at first, but at last it will try to settle. At first there will be some oscillations. At first there will be some oscillation, but over the period of time it tries to decay. Critically damped in the sense there will not be any oscillation. It is a kind of ideal scenario. At that point, when the damping, or when you leave the door, it will just close the door without any action. This is ideally not possible, but at some perfect system we can make it. Overdone in the sense it will be too slow, very slow, but it will never reach the point, and its amplitude decays over time. So these are different characteristics of the system. So in this case, undamped system, you will see the oscillations are there forever, right? There isn't any decay you can see here. In this case here, in case of overdamped system, you can see the amplitude decays and tries to settle. But this underdamped case is some good case. Most of the applications will be here. At first there will be some oscillation, but it tries to settle at that. Okay. This is the examples of simple pendulum at different cases. In undamped case of simple pendulum, it will be like that. It keeps oscillating. It will be simple pendulum in the sense the one pendulum will hang here. It keeps oscillating here and there. It will never try to settle here. There will not be any damping or there will not be any spring here. But in overdamped case, if you take the pendulum here and you leave, it will take so much time to be here and there will not be any oscillation. Once it comes here, it will try to be here. But it never, you cannot say that it is 0 degree, it's at 0 degree, it might be in 5 degree, 10 degree. This is overdone. The spring, too much spring action will be there that it won't let it come to the 0 degree. But in underdamped case, the oscillation can be there and at last try to settle at 0 degree. Okay. Now, if people are clear what is underdamped, undamped, overdamped, or critically damped system, they are okay, right? Oh, good. So now we are coming to the point why we need a Laplace transform. So till now we have seen what is time domain, what is frequency domain, right? Now we have another domain called X domain. Dhruv, you have any doubt? Okay. That doesn't matter, that doesn't relate to the undamped overdamped case, but natural frequency is this how efficient it is. For example, if it is oscillating too much, at what frequency it is oscillating, that is being represented by the natural frequency, that's it. But that doesn't add anything to the cases, whether it will make the system undamped, overdamped, or critically damped, underdamped. Okay. Dhruv, is it clear? Right. So far we have seen time domain and frequency domain, some of the characteristics of those domains. Now we are going to see what is S domain. S domain is the, it's a representation of sigma plus j omega. For example, sigma is that, sorry. So we are now trying to combine both exponential signal and a sinusoidal signal. So Laplace transform decomposes a signal from time domain into a domain of both sinusoidal and exponential function. Instead of looking into only one sinusoidal signal or additional sinusoidal signals as in Fourier transform, we are trying to move forward or elaborate the study by including exponential function also, so that we can study the property of the signal or the system in detail when compared to only the sinusoidal function. So here you can see, to account for exponential responses, we will extend the idea of frequency domain representation to the S domain representation. There is no such thing called this is superior than this. These are all two different tools. You can see in that aspect. At some point Laplace domain will be helpful. At some point Fourier frequency domain will be helpful. Okay. This S domain is again can be called as Laplace domain also. Don't get confused with these two. Okay. So as we saw in Fourier transform, this is the mathematical representation of the Laplace transform. So this is the original signal that will be always multiplied by 1 e power minus st, where s represents sigma plus j omega. It's composed of this of t. Okay, with respect to time, how this will be, this is reiterated. Okay. Then comes, as we saw, there will be properties for Fourier transform signals. There will also be properties for Laplace transform, which will make our calculations easier. So when you say, again, we are familiar with this impulse functions, right? So when we want to see the Laplace transform of the impulse function, it will give in S domain, if you represent in time domain, if the impulse response is like this, in frequency domain, in Laplace domain, the impulse response will be like this, same. It will be of magnitude what, that's it. Laplace domain will be looking like this. Okay, where in time domain it will be t. Okay, how the exponential signal, exponentially decaying signal will look like. Here, so when you integrate this to, so since it is a exponential signal, you can make it, write it as e power minus s plus ap, right? So when you integrate this, when you integrate an e power x signal, it will be e power x. When you integrate a minus e power x signal, it will be e power minus x by minus 1, right? That's how it was written, e power minus x by minus 1 at the limit. The limit can change with respect to the system, whatever system. If you are looking for a finite domain, you can make the system to 0 to t. Otherwise, it's an infinite time you are trying to calculate for the infinite time. So if I put this 0 to infinity, e power minus infinity, it will be 0, e power 0, it will be 1, right? When it is e power minus 0, this will be 1 by s plus c. This will be 1, this term will be 1, and minus minus will get cancelled, this will be only the s plus c, where this s plus c will be greater than 0 for sigma plus a greater than 0, when the sigma it will at this domain. At this domain, when sigma will be greater than minus a, if this is minus a, then all this domain will be positive based on this. Similarly, the Laplace transform of signal t, that is ramp signal, then it will be 1 by s square. So for impulse response, Laplace of impulse response will be 1, Laplace of step signal will be 1 by s, Laplace of ramp signal will be 1 by s square. So it goes on. Say impulse response will be delta t, u of t will be equal to 1, u of t will be equal to, r of t will be equal to t. So in time domain, if this is an impulse, in Laplace domain it will be 1. In time domain it will be 1, it will be 1 by s. If it is t, the Laplace domain will be 1 by s square. Similarly, it will go for parabolic signal, the Laplace of parabolic will be 1 by s square. These are all ready-made calculation where it can be defined using this formula, that's it. Instead of calculating every time, we just have calculated this, and you can keep this in mind when you are doing your problem. So this is one example where you find the Laplace transform of a sine at. So this could be taken as a homework, where you will this sine at will be represented in terms of exponential signal, e power at minus e power minus at divided by 2 omega. Okay. So based on this, so once you calculate this, just multiply it and take the common powers and make this as a 2 separate integral, and as you do to the previous thing here, as you do to the e power minus at, you will do it twice, that's it. That is the difference between these two, and you will get an answer like this. Similarly, find what is the Laplace transform of cos at, tan at. Right? This is the answer for this. So ready-made, it's a kind of ready-made recipe. Whenever you want to find a Laplace transform of s sine of at, you can just straight away substitute this, that's it. But you should know how this comes using this formula, that's it. You should be able to derive it by yourself. Once you practice this, straight away you can use this. Instead of mugging up, this will be helpful. And some of the properties of Laplace transforms are, Laplace transform satisfy linearity. Linearity in the sense, if you multiply two input signal by a constant and add it together, that will be equal to individually taking Laplace transform and multiplying and adding by a scalar and adding it together. Time shifting, whatever time shift you do in the time domain will be represented as a power of the exponential signal that is being multiplied. And time scaling, if you scale the time, for example, if you reduce the time or increase the time, that will be affected in this format, 1 by t, that we have already seen in convolution property, is very similar to that. Some other properties that you have not seen so far, this is time differentiation and time integration. These are all very important formulas. When you integrate a signal or when you integrate a when you differentiate a signal and take a Laplace transform, you do it like this. So based on the order of the signal, this will get extended, right? If it is a single order differentiation, then it would be x of xs minus x of 0, where x of 0 is the initial value of the signal. So this will be the differentiation of the initial value of the signal. Likewise, whenever your order of the differentiation increases, this will also be increased. X of s is the Laplace transform of the particular signal. Frequency differentiation and frequency integration are also another properties of the Laplace transform. Please focus on these properties and try to solve few problems based on that. We will be giving that in the assignments also. And another important theorem in the Laplace transform is the initial value theorem and the final value theorem. Initial value theorem says whether it's a way to determine the initial value of the time domain function directly from its Laplace transform without needing to perform inverse Laplace transform. Only with the Laplace transform we can say what will be the initial value when it is applied on a time domain. That is the one tool or one theorem you can use, that is initial value theorem. For example, when you say limit t tends to 0 at x of t, that will be limit s tends to infinity in the Laplace transform, s into x of s, where x of s is the Laplace transformed value. By seeing this will make you think like you will know this, but when you try to solve problem, you will try to see the problem there or the difficulties there. So I would recommend you to take some problems, try to solve by yourself without getting any help. Then only you know where you are struggling. Then you can correct that aspect. Okay. So this is some example. For example, if I take a signal as 3 plus 4 cos t, when I try to find the initial value where I have started the signals, so I would try to apply that wherever there is t, I will try to apply 0 to that. So when I will say initially I have started from 7, value 7. So in this signal initially I have started from 7, right? Cos value, right? This will look like this. And in S domain, how we can easily do that is, if you know the signal, you know what is cos AP, right? For cos AP, it will be S by S square plus A square. So this A is cos AT, here cos 1t, it will be S by S square plus 1. Since it is 4 cos AT, it's 4s by s square plus 1. That's what I written here. Since you know the shortcut or the answer for this beforehand, you would straight away solve this. And you know for 1 is unit step, u of t is equal to 1, then in Laplace of u of t will be 1 by s. So since it is 3, it is termed as 3 into u of t, then it will be 3 by s. That's why it is 3 by s, 4s by s square plus 1. So for this, you will straight away add s is equal to infinity. So if you take the s common here, and if you put s is equal to infinity, this will be 3 by infinity, that will be 0, 4 by 1, this will be, oh, this s will be cancelled, right? 1 s, then this will be 1 by s. If you take the as a common, I think we will be able to use this element. Okay, but I'll try to show it here. Okay, then if I take that will be 1 by s, this will be s. When I remove all the s's, then you will get 3 plus 4 equal to 7. Similarly, similar to initial value theorem, there are final value theorem also, where you this will, instead of giving the initial value, this will give the final value. There is no much difference. So whenever you want to try t equal to minus t tends to infinity, here you will just replace s with 0. That's it. In interest of time, we will just quickly go through lecture 4. So far we have seen what is Laplace transform. Now we are going to see what is inverse Laplace transform for some reasons, because for some signals, if you want to find the original system back from the transformed signal, you would need this too. So there you saw the equation as x of t integral 0 to infinity x of t e power minus st dt, right? Here the inverse Laplace transform is represented by 1 by 2 pi j integral e power st x of s into ds. Since I couldn't show, I am just spelling it out. Similar to Laplace transform, there are some properties for inverse Laplace transform where you have to learn this so that it will be easy while solving the problem. Just see how this works. Take one problem and see if it is time shifted, how you can use this property. If it is time scaled, how you can use this property. Just one line will be easy. You just have to straight away use this formula and get back the original signal. That's it. Another thing is, in time domain, while doing convolution, we saw if we want to convolute two signals, for example x of t and h of t, the convolution will be integral 0 to t or 0 to tau x of t h of t minus tau d tau. That's how complicated it is in time domain. So convolution is free. S domain will be very easy than the time domain. Convolution in S domain is a multiplication of convolution in the time domain, right? Instead of doing all the shifting and scaling in the S domain, we will just multiply two signals. That's it. That's how simple and easy it is. Just like as in frequency domain. Okay. If I want to convolute two signals in time domain, I will find the Laplace transform of those two signals and I will just multiply it. That's it. Instead of doing all those steps, time shifting, scaling, everything, I will just find the Laplace transform and multiply it. So this is one good application of the Laplace transform. See, it is complicated. Doing all this sin tau into t minus tau, calculating all those things and doing integration will be tougher. So I will just straight away find the Laplace transform of sin t and u of t and I will multiply it. That's it. And here you have to do some partial fraction to find the original answer. And if you are asked to solve only the Laplace transform, then it is fine. If you are asked to find the signal back, what is the time domain signal or convoluted signal in the time domain, we just have to apply another inverse Laplace transform. That's why we are studying the properties of the inverse Laplace transform. Similarly, it will be helpful in solving ODEs, and that will be that ODE become linear equations here. That is ODE will be very handful to solve. So here it will be only the linear equation. For example, d square x by dt square. The Laplace transform of this will be just s of x of x. Sorry, s into x of s minus x of 0. If the initial condition is 0, it will only be s into x of s. That's it. So here, since it is d square by x, this is s square. 2 into d of x become 2s minus 1. That's it. It will be very simple equation. Instead of doing all the differentiation and putting the constants, this will be a linear equation. Just you need to know what the initial conditions are. That anytime, anyhow you have to find that. One example, we have seen this previously, right, in the convolution. So this is equation 2 represents the output of it. We cannot guarantee that whether that is the only solution of that. So for that convolution comes into the picture. So this is another way of representing in S domain, how S domain is helpful in confirming whether that is a solution for that equation. That is being expressed in the equation after the Laplace transform on the right hand side. Same, solving ODEs. There will be problems in this aspects. As we see here, we saw some simple example, right? Similar to this, if we have increased the complexity, let's say y double dot. This is b squared y by dx squared minus 2 dy by dx minus 8y. That's it. Instead of 8, it is 8. How we are going to solve? We have given the initial conditions, just we are going to apply this Laplace transform. For y double dot, it will be s square y of s minus s into y of 0 minus y dot of 0, since it is a second order system. For 2y dot, 2 into s into y of s minus y of 0, only one initial condition is enough. For 8 into y of s, it's simply y of s. That's it. 8 into y of s. So after you get a linear equation, after you applying all the initial condition where y dot equal to 6, y equal to 3, after applying all these things, you will get a equation like this, where capital Y of s is being represented. When you do partial fractions, you will get the answers, Laplace transform of it. Or if you are asked to find the original time domain representation, just do an inverse Laplace transform. That is this y e power 4t plus e power minus 4t. So here it was asked one quick question: what is the final value and initial value of the system? Can we find this final value or initial value of the system? Can we find it? Or if yes, how can we find it? Can people answer? Are you guys with me? Thumbs up or thumbs down? Can you please do that? Yeah, y of t, t tends to 0 and infinity. So yeah, right, you can do that. But as we are having this Laplace transform tool, we have just you have this y of s, right, time domain equation. It will be easy for you to put only s equal to infinity to find the initial value and s equal to 0 to find the final value. That's it. You don't need to put t equal to infinity or t equal to 0. So that will be kind of giving an exponential and it gives 0, infinity. You will not find value as quick as the Laplace transform. Okay, that's it. Just use the initial value and final value. Fine. We are end of the lectures of the week 2. So far I have given some gist about this. So with that we will try to attend a quiz. It's a kind of fun game, and just try to see. I was just trying to understand how will you understood this lecture and discussion. I will share my screen. Okay, everybody is with me, right? I'm sharing my screen. Is this visible? Yeah. Okay. Just take your phone, or if you are using your phone, just screenshot this page and go to this QR code. I will wait until you all join. If you have spare phone, use the QR code, scan the QR code from that phone. Otherwise, take the screenshot of this QR code and go to that website. Go to that link. Otherwise, use this link in your phone, menti.com, and use this code to join. Five people are there. I will wait until you all join. Only three join. Oh, who are all the three who didn't join it? Okay, another one waiting for you. Join quickly. Type your name and join. Anyone is having difficulties in joining? Oh, okay, right. 5 players. Okay, I'm going to the next question. Answer quickly as possible. First, think what is that signal x of t equal to t. So you should think that as t into u of t, where u of t is equal to 1. Everybody responded? Right. Okay. I'm going to move to the next question. Okay. If you convolve two ramp signals, what type of signal do you get? There will be timer. You should respond before that. Now it is taking time. Respond quickly. One person hasn't responded yet. What is the Laplace transform of 1 into u of t? Next time I am going to reduce the timer. Sorry for that. What's the answer for this? It is 1 by s. So it is a unit step signal. Laplace transform of unit step signal is 1 by s. Laplace transform of impulse signal is 1. Laplace transform of ramp is 1 by s square. Parabola is 1 by s cube. Right? For the previous question, convolution of two ramp signals would be parabola. And the first question, what is the derivative of that signal? If you take the t into u of t equal to 1, then it will be 1. It will be like a unit step signal, ramp signal. If you you find the derivative of the ramp signal, then you will get step signal. Okay. Thank you. This will not be calculated for marks. Just I want to get some interest out of you so that you will learn more in the upcoming sessions, and it will be interactive to know how much you understood from the session. Okay. I will also be working on how well we can make you interact with each other. So if you have any doubts in today's session, you can ask me. Otherwise, we can meet on Wednesday. Anybody has any doubt? Thank you. So if you have any feedback, you can give me, and we can make it work for the next time. Anybody have any doubts? Google Space, I think yes, it has been made for computer engineering. I can ask my team and let you know in the next session. We quickly take attendance. Please turn on the mic and respond. Okay, Vinayak. Hariom. Jamila. Sayan. Duru. Okay, thank you. You can leave if you don't have any doubts. Thank you for joining. Thank you. Jamila, do you have any doubt? Okay, it's been recorded. I haven't uploaded the link. You will get the link shortly, okay? But we have missed 2 sessions to record. The rest of the sessions you will get, okay, hereafter. Okay. Thank you, Jamila.